Okay, good afternoon, everyone. Welcome to Physics Day 2022. My name is Amara Bihari, and I am the Physics Department representative on the Student Council, as well as the Vice President of TTSPARC. Today, I am accompanied by Ms. Kyra Paul, Deputy Physics Department representative on the Student Council. We would be taking you through today's festivities. Initially, we were going to stream on 2 platforms. However, just one platform was corresponding with us. So we would add a recording to the council's YouTube page, which you can view at a later time. This event is intended to motivate, inspire, and encourage students interested in and already a part of the physics community.
For today's event, we have a very packed schedule. So to keep your attention, our committee has decided to play a game. Instead of a traditional Jeopardy at the end of the event, one of our club presidents, Mr. Orain Green, will be asking questions throughout the event. The way it would work is that the question will be asked and you will be counting down from 5 seconds so that each person has time to be able to type out their answers. And the first person to give the answer right or the correct answer will be awarded 3 points. The second person to do so will be given 2 points, and the third person 1 point. A total of 5 questions will be asked, and the top 3 persons will be given prizes. However, there's a catch, and that is that we won't tell you exactly when we will ask these questions, so you have to pay attention if you want to win those prizes.
So when we have a question, this is what will happen. And we will now have Mr. Orain Green with the first question.
So hello, everyone. Greetings from Jamaica. So the first question I have is, who can tell me what are the 4 states of matter?
Five, 4, 3, 2, 1. Yeah. No problem.
Okay, so your answers will be recorded by our chat moderators who will introduce themselves. But for now, we will continue on in the program. So because this event is being held by the FSTSC, which is the FST Student Council, we would like to begin our event with a fitting introduction from someone who is a spearhead in our department. That is none other than Dr. Devinder Sharma, the HOD or head of department and a lecturer in electronics. He graduated with a Master's of Science in Applied Physics and a PhD in Communication Signal Processing from Guru Nanak Dev University in India. Some of his research interests include digital signal processing, smart grid technology, and the design and modeling of renewable energy systems. It is thus fitting that I welcome Dr. Sharma to deliver the opening address for this event. Over to you, Dr. Sharma.
Thank you, Kara and Amara. Okay, so thank you very much. Good afternoon, everyone. So, dear Dr. Sharon Huck, Senior Lecturer in the Department of Physics and keynote speaker for today's event. Other academic members from the department and presenter, Dr. Roger Andrews, Dr. Nikolai Zuzikov, and Dr. Andrea Joseph. FST representative on the Guilds of Students, Mr. Jeremiah Mathura. Physics representative from FST Student Council, Ms. Amara Bihari and Ms. Karapal. Presidents from the UV Stargazers and Spark Clubs, both TNT and Jamaican section. Physics students from the St. Augustine as well as Mona campus of the UWI. Ladies and gentlemen, on the behalf of Department of Physics at the St. Augustine campus, I welcome you all to the today's Physics Day event of the FST Student Council. I'm very pleased to see the effort of our students and clubs, even in this pandemic. Co-curricular activities, especially during these stressful days, can play a vital role in your personality development and can give you new energy to achieve your academic goals. I appreciate the hard work of Mr. Mathura and his team to bring all physics clubs together and organize this cross-campus event to further strengthen the One UWI mission. Department has been supporting its club under the mentorship of Dr. Hart and will continue to encourage their activities. I know our students are working actively on starting new UVSTA electronics club and hoping that it will hit the ground by the end of month of March. Department is willing to support all its students club and provide necessary resources. It will be great if a technical festival can also be organized, including events like paper presentation, programming and circuit designing contest, innovative projects or idea and their presentation, debates, including debates and some cultural events. Such events prepare you very well for the world of work and increase your chances of success. I would like to congratulate the FST Student Council, especially the student of Department of Physics, for organizing the Physics Day and wish them a huge success for today's event. I wish to thank very much to the academics member of the department for supporting our students. Thank you all, the presenter and the attendees. Please observe all COVID protocols and stay safe. Looking forward to see our students face to face again. All the best. Thank you very much.
Thank you, Dr. Sharma. Being the Vice President of TTSPARC in my second year, as well as the first year representative in my first year, I can definitely say it is very important to have more than academics in your university life. Although we are limited due to COVID-19, our clubs and societies in the department and the faculty have found many ways to communicate with their members, so we look forward to knowing more about the Electronics Club come the end of the semester. We know that you're very busy, Dr. Sharma, and we sincerely appreciate your presence throughout the event. Moving right along with the agenda, we now have a short greeting by our FST representative and president of the Student Council, Mr. Jeremiah Matura.
Good afternoon, students of FST and the great physics department. As my counselor introduced, I am the Gale FST rep. But let's not only focus on that. I am one of you. I'm a physics student. I'm trying to complete my degree, hopefully by the end of the semester. And being part of this amazing department has afforded me many amazing opportunities. Me being in this department was never a short decision. It was a very tough decision for me. I didn't even do physics at Cape. But my decision to come into this lovely department is one that I will never regret. I have been afforded the opportunity to learn a lot of things about the world, the universe, that I would have never learned if I had gone into medical engineering. I got the opportunity to be in several clubs, served as the PRO for TTSPARC, and then in my final year, I haven't been elected as the Gale FST representative. I'm now using my talents and responsibilities not only to represent the students, but to use platforms like this to allow students to know when you come out of FST and when you come out of your respective departments, your future is bright. And we have been working with the clubs, all in all departments. And because it's Physics Day, I only stick to TTSPARC and Sagezas. We've been working with them, expanding the clubs to ensure that every student is aware of what the future holds for them. And I thank you all for coming to Physics Day 2022. This is the first time an event of this caliber has been held by this administration of the Student Council. And though COVID has greatly limited what the council and these clubs could have done, we will be using the online apparatus, which we're using today, to see how great these events could turn out to be. And I thank you all. I hope you have a great session going forward. Back to you, Amara.
Thank you, Mr. Matura. So as Mr. Matura would have mentioned, the physics department has two physics clubs, which are TTSPARC and UE Stargazers. So to start us off, we will have Mr. Brandon Mohammed, TTSPARC's club president for the past 2 years. He has played a very integral role in the development of the club by working with the team of the previous executive, as well as persons from our sister campuses in Jamaica and Barbados. 2 sister clubs were established. Invited to today's event, you'd see Mr. Oreen Green, president of JAMSPARC. So let's hear from them.
Good day, everyone. Thank you for that introduction, Mara. And I am so happy to be here with everyone. I'm so happy to see that this event has come forth. It has been a dream of ours since coming in, and I'm happy that there are many of you watching on our Facebook. So I hope that you enjoy today. I hope that you enjoy what we have prepared for you all. And I hope that you walk away knowing that, as Jeremiah said, when you graduate, your future is bright, and that there is a lot that we can learn from physics. I pass it to Uri.
All right. Hello, everyone again. Greetings from Jamaica. As you would have heard before, my name is Oreen Green. I am the president of JAMSPARC. I would just like to say I'm so appreciative and so happy to be here. You know, this is what we like to see when it comes to the diaspora and talking about physics, because physics is so important. When I ask students today, what do they think or what do they know of physics? They tell me a lot of things, but the way I see physics is the intrinsic understanding of reality. And who wouldn't want to understand how reality operates and works and utilize that to its best and fullest ability to work for us human beings who are able to experience life in this form and in this way. So I hope you get a greater understanding from what we're going through today and understand the importance and the excitement around physics. Back to you, Amara.
Thank you, both presidents. Unfortunately, Stargazers would not be able to attend the event today, but they do send their apologies. So, question time. Oreen, let's hear question 2.
Yes, absolutely. So I would want to ask, what is the difference between weight and mass?
Five, 4, 3, 2, 1, go.
Was anyone able to guess it or get it? It's a simple differentiation. I would assume. I would believe.
So we'll give you another 5 seconds to type an answer. Think about it. Think about what you've heard in your classes.
Come on, guys. So what's the difference between mass and weight?
Try to remember your lecturers speaking in class.
We got some answers. Let's
Wonderful.
see.
So your answers will be noted by our chat moderators. So for now, we will move on. Our keynote speaker for today's event is none other than Dr. Sharon Hack, astronomer and senior lecturer at the University of the West Indies in Trinidad and Tobago. She is a former head of department of the physics department and deputy dean. She's the recipient of several local, regional, and international teaching and science research awards. Her areas of research are in cosmology and astrobiology. With an MPhil in psychology, she engages in cross-disciplinary research as well. She's the first woman to receive the CARICOM Science Award, laureate of the prestigious Anthony N. Saber Caribbean Award for Excellence in Science and Technology for 2020. She has produced several Caribbean science documentaries before going on to host the series on Let Be, Exploring Our Place in the Universe, and Full Steam Ahead. Due to COVID restrictions, she now has a YouTube channel with astronomy and science content for children and adults. She's also the editor and producer of the magazines The Intellectual, Art, Science, and Architecture, Eureka, and Wish Upon a Star. She's the co-founder of the Caribbean Institute of Astronomy and founder of the CEO of the Wish Foundation. Also a co-founder of the Caribbean Astronomy for Inclusion. She is a national outreach coordinator with the International Astronomical Union and director of the UE-NRAL 9 Hub of Satu Observatory. Her fun career high points include getting an exoplanet and star named by Trinidad and interviewing then Professor Jocelyn Bell Bunnell, discoverer of pulsars. We welcome you, Dr. Hack.
Good afternoon, everyone. Thank you, Amara, and to all the wonderful students who are out there, and those of you that are part of the FST Council and the wonderful societies that you have made happen. I can't begin to tell you what a joy it is to see it. Orin, you have no idea what it does to my heart. You may not know a long time ago, we are one of the original co-founders of SPARC itself. To see it spread its wing to the Caribbean is a most marvelous thing. All right, guys, so thank you, and to all my colleagues who are here and everyone else out in the virtual world, let me get started. Okay, so I'm going to share my screen at this point. Okay, so one of my favorite quotation is, somewhere something incredible is waiting to be known. And if you have had any interaction with me in my classes, you're probably rolling your eyes. You know who probably said that. But today we want to see a little bit of how this extends specifically to physics and astronomy. And who would have said it? None other than, of course, the great Carl Sagan, who was absolutely instrumental in inspiring me. And that's where you see the importance of mentors and people that you work with. And it can be people on television, anywhere, that can actually inspire you to take the path that you proceed to. And Carl Sagan played a big role with his series on Cosmos many years ago. And he says, if you want to make an apple pie from scratch, you must first invent the universe. And of course, I have my local take on it because we're not into apple pies, right, in the Caribbean that much. So if you wish to make an aloo pie from scratch, you must first invent the universe. And that is as real as anything can get. And right there, you see the huge range and the impact of physics in everything. Just in that statement, I could end my talk right here, but I have a couple more minutes, I've been allowed. So folks, meet the boundless Ouroboros. The theme for the this afternoon's presentation was really about that physics is boundless. So I ran with that theme, and I hope I can show you in the next few minutes that how, like the Ouroboros, and you're wondering what's Ouroboros, and you're wondering if you'll remember how to spell it. Okay, so that is, as you can see in the image there, it's a mythical creature. You can say it goes back to the Mayans and so on, where the head and the tail come around and a circle is completed. And pretty much what that does is, where's the beginning and where's the end? And I think it is a good way to visualize and to understand the power of physics. I think there is absolutely, let's see if I pull up my pointer. Okay, yes. there's absolutely no discipline that spans to the order of almost 10 to the 40, scales of 10 to the 40. And at the smallest scales, and right now for the first time, we've launched a brand new course in Department of Physics, and several of you here are doing it, Fundamentals of Atomic and Nuclear Physics. And you learn that it's physics alone that could truly understand what's happening at the smallest scales of the nucleus, high energy particles and whatnot. And as the scales get grander and grander to us, the human, the mountains, the earth, and the sun, every aspect of physics is involved there. And here, right here in Trinidad, in our Department of Physics, you are going to be dealing with environmental physics and all the different things. And of course, as you may have picked up, by profession, I'm an astronomer. So that, well, of course, to me, the heart and soul of physics, right? The Earth, the sun, the galaxies, the solar system, and on to greater and greater and greater scales. The further out we can see, the further back in time we are looking. And therefore, we see the beginning when we can see as far out to the end as possible. So you can see why the Ouroboros makes a very interesting analogy for the range of the things that physics can capture. I am the beginning of everything, the end of time and space, the beginning of every end and the end of every place. What am I? Memorize that. I am actually asking you that, and do not answer it yet. Do not answer it yet, but when I'm finished with my presentation, I will cue you to respond to this, and you can win this handy dandy, designed by me, handcrafted pencil case, right? Which student cannot do with a pencil case with that, right? As you can see, the most beautiful equation of all in physics, E is equal to mc squared. So do not respond now, at the end of my presentation. But I have left this slide on for a little bit. Take a read again. I am the beginning of everything, the end of time and space, the beginning of every end, and the end of every place. What am I? So in trying to bring the awe and wonder and magic that I personally feel for physics, I decided to see where the impacts of physics has been, right? And of course, when you say physics, it's mathematics is not too far away. So there's this remarkable book called The Great Equations, and it highlights 10 equations, all right? Start taking notes, people. It's not coming for exams, okay? 10 of the most beautiful equations in the history of humanity. And as physics students, all the 5 of them that you are seeing there should all look familiar. No one can get past the Pythagoras theorem, the basis of civilization. The high point of the scientific revolution was when Newton was able to explain the gravitational forces. The second law of thermodynamics, known as the scientific equivalent of Shakespeare. And all of these things led to the burst of the Industrial Revolution. The soul of classical mechanics, F is equal to ma, right, Orin? Not gonna say much more. And these are just like 10 of the most beautiful equations in mathematics, right? So there's Euler's equation, absolutely. I could just give you an entire lecture on each one of them, but that's for another time. So 10 equations, here's another one, and that's what E is equal to mc squared. The famous Schrodinger's equation, the basic equation of quantum theory. Of course, this is the celebrity equation because it is the most famous equation of all times. And of course, the most significant event of the 19th century was really the understanding of electromagnetism and how they could be shown through Maxwell's equations. And just when we thought we understood and we knew everything and we had nailed it, came quantum mechanics and the Heisenberg uncertainty principle. And the most famous scientist really of all of them, it was not enough. that he had developed special relativity. It took another decade, a little bit more than a decade, to truly understand what gravity is, and how you can describe structure in the entire universe. And that came with Einstein's, one of his equations for general relativity. Here in 2 slides are humanity's greatest feats. And like I said, it's not coming for exam, but what I wanted to show you here is that when scholars pick out the most powerful mathematical equations, they're all, this is when I miss my real audience, because I'd have you, and I hope you've all said physics. Almost all of them are physics. So then I went to seeing, what do people in all fields consider 5 revolutionary ideas that changed the world? And of course, it's absolutely not easy to bring things down to 5 and to 10 and things like that, but that never stops anyone from trying. And this is what I found, that some of the most revolutionary ideas that changed the world, that allows us to be even engaging as we are right now, was, there you go, special relativity. It's physics, people. I mean, we are so honored to be part of being able to engage in such an enterprise. Quantum theory, those are the associates with it. Number 2, and what is this we have here? Charles Darwin, right? Remarkable input in understanding the evolution. So Charles Darwin is right up there with the change. Number 1 was, after thousands of years of believing that the Earth was in the center and the sun went around it, it took one person, one scholar, Copernicus, in 1500s to put forward the idea, at the risk of death and being committed for blasphemy and things like that, and charged with heresy, came up with the idea, thought, no, truth cannot be that. Truth is that the sun is in the center and that Earth goes around it. You know what I'm saying here, right? 5 revolutionary ideas, 4 of the 5 belong to physics. And yes, in the Caribbean, we don't have a mountain like this, but it's a pretty famous mountain, Mount Rushmore in the United States. And here we have, these are things that you can come across, some of the greatest scientists of all times. And even if you ask children, who are they? And of course, right? The most recognizable face that we can all know, Albert Einstein. It might take a little bit of staring to figure out maybe who the others are, but this is actually Marie Curie, radioactivity, physics, yes. Newton, of course, is never too far behind Albert Einstein. And yes, we have a Confederate again. We've got Charles Darwin with us, because evolution, even though this is a session on physics, is a powerful idea that helped us to understand things. So then I moved to, okay, revolutionary ideas, greatest mathematical equations. Come on, physics can't be nailing all of them, right? So let's go look to see what are the top 5 inventions of all time. And this is what I pretty much came up with. Optical glasses, right? And that was like in just around prior to, well, 1600s. Semiconductor electronics, penicillin, electricity, and the printing press. And you're starting to see a pattern here. Optical glasses, of course, led to the invention of telescopes. And you know what that has done for our ability to see very, very far distances and understand the universe. Semiconductor electronics, that changed. I mean, what we are able to do right now is because of the transistors, and which led to the development of the miniaturization of things and computers and whatnot. Which discipline did that come from? You got it, physics. Penicillin, no, right? We have to be healthy and well, right? So penicillin rightly deserves to be right up there with eventually antibiotics, because of what it did for the field of medicine and human well-being. So it is in one of the top 5 inventions of all time. And nothing today is possible. And the impact that electricity had on humanity as a whole, like I say, each one of these words could be entire lectures. And the printing press, yes. So in the 1500s, the Gutenberg printing press came around, and that allowed information to reach masses. So today I would translate this to the internet. And the internet, what are the disciplines involved there? Well, you guessed it, okay? Again, physics in terms of ICT and so on is a powerful role it plays there. So we're nailing it, people. Inventions, ideas, mathematics, and then everything that I've shown you within the last few minutes, it's like, well, you know, yeah, modern physics belongs to the early 1900s. So question is physics over? All right, so I borrowed the words from Stephen Hawking, right? A very well-known physicist, astrophysicist, cosmologist. The world has changed far more in the past 100 years than in any other century in history. The reason is not political or economic, but technological. Technologies that flow directly from the advances in basic scratch physics. Technology actually stems from understanding of basic physics. Clearly, no scientist represents those advances better than Albert Einstein. So he had noted this at the time of when Albert Einstein was the man of the century. And just a quick trivia, which I get pretty fascinated with, right, is that did you know that Albert Einstein, he was born on March 14th in 1879, and Stephen Hawking died on March 14th, 2018. Right? Coincidence, but it's remarkable, the connection. So physics is boundless, as you, the students, have kept the theme of this session. And I ran with that theme with the Ouroboros, which you are seeing here. And I'd like to say that when the end is in sight, the journey has only just begun. So the question is physics over? Because all the fundamental physics, last century was the century of physics. This century is a century of biotechnology and bioengineering and things like that, okay? But guess what? The journey has only just begun, because the Webb Space Telescope was launched just recently. It reached its million-mile mark out in space. It's remarkable, the engineering here. Space tourism has kicked off. All of this is based on the physics we was trying to understand all those decades ago. Quantum computers are making headway. Other new missions are going to be going to the moon and landing people once again on the moon, something they've done already. And we are on the verge of cracking the code for fusion. And once we have fusion, our energy problems are pretty much over. Graphene material. And I hope that maybe one day that we have a new lecturer in our department, Dr. Right, he's with us, and sorry about that, the name slipped me here, Dr. Pathak. And his area is in materials, and maybe you can listen to him talk about graphene. It's remarkable, it's changing everything. So while biology is now kicking off, we in physics have a 100-year start on them. So biology is now where physics was 100 years ago. And because of how physics has changed the world, it has literally plummeted us into the space age. So today, people, we live in an era where technology is no longer a luxury, it's a necessity. And I want you to understand that once it's technology, it's a necessity, The base of it is the exciting feature of physics is its capacity of predicting how nature will behave in one situation on the basis of experimental data obtained in another. Such predictions place physics at the heart of modern technology. You live in a technological era and its heart is physics. I don't have enough time to be able to tell you that with a degree in physics, what you can leap off into. You can leap off into practically anything that for this modern era. So my dear students out there, I did not want to disappoint some of you who may know exactly where this is coming from. And those of you who do not understand, in some of my classes, we sort of very much slip into speaking in what we also call Yodanese. And I will be ending with, to all of the students out there, great things you must do. The future sees you must. Standing at the edge of a new frontier, we are. And folks, that brings me to the end of my presentation. And I had mentioned that there was a little something for you to figure out the riddle. So you are welcome. I hope you took a screenshot of what was written there. And that's why I left it. And I told you, read it, reread it again. And you're welcome to attempt it now. And with that, let me pass it back over to Amara, as you're the chair, right? Okay, thank you.
Yes, Dr. Hack, thank you so much for that very intriguing presentation. I know I had the privilege of having one of your classes, so I know how easy it is to slip into those yoga words, yoga words, sorry. So Dr. Hack did say that she had a question that she asked. So I'll give you all a chance to give your answers in a few seconds.
Yeah, if there are attempts, if not, I could put back up the slide very briefly.
So we have, I'm going to start counting down now. 5, 4, 3, 2, 1, go. Okay, I'm assuming that there are answers coming in on the live stream.
Okay, so there are, that's all. Yeah, once there's answers.
Yes, I believe there
are. Okay.
So we'll move on now. A great part of your university life is being able to speak with your lecturers, whether it be having difficulty with a specific concept in a course, or even doing well on an exam when you thought you'd possibly fail it. I had the privilege of having Dr. Joseph as my first year advisor. She is a physicist who is passionate about her field and working with young people. Think, explore, learn, grow, serve. That's her mantra. While there's no greater love for her in the field of science and physics, she's quick to note that this was not always the case. But as she's always eager to tell others, if you want to give yourself options in life, never be too quick to close the door on what has been placed before you. And using John Maxwell's words, she found her purpose, her why, and her greatest way to make a difference. She sees in each young person the potential for greatness, and it is primarily because of this that over the years in her professional and private life, she has willingly and enthusiastically worked with young people and mentored them in the discovery of their own potential and in the development of skill sets and attitudes that will be beneficial to the society now and in future. She's had the privilege of serving as a member of staff in the Department of Physics in various capacities over the years and has striven for excellence in the dissemination of her duties. As coordinator of the Department of Physics BSc program in Biomedical Technology, she has established working relationships with both public and private healthcare institutions. So spearheaded the securing of internship positions in these healthcare institutions for over 100 students as part of their undergraduate program. Her current research interests are in the areas of quantum optics and medical physics, and through a number of collaborative efforts is excitedly pursuing such research. However, due to connectivity issues, we will be sharing her pre-recording. I will share that now.
Good afternoon, everyone. The organizers, the chair for this afternoon, our keynote speaker, other invited speakers and presenters, invited guests, physicists, and all persons interested in physics. To the organizers for this event, thank you for the opportunity to speak. Now, if you've been in class with me long enough, quite likely you would have experienced one or both of the following: my singing a phrase or question to you, and my use of the phrase life lesson while making some point. Well, thankfully today, we'll focus on the latter. Now, you have chosen today to celebrate or commemorate or feature physics. What does that mean to each of us, though? What is physics for you? Maybe it represents a path that can lead to a dream career, financial security. Maybe it represents having an openness of mind to the minute or the macroscopic. Maybe your excitement for physics comes from being able to use it to understand so much of what happens around us. Or maybe, as I want to focus on for a few minutes, we are tipping our hat to the wonderful versatility in physics by acknowledging the life lessons that we can learn from physics. Now, there are so many examples in physics from which we can draw these life lessons, but I just want to share two with you today. One, let's start with the minute. How many of us know about quarks? So let's talk about quarks. How many do we have? We have 6 types or flavors. Yum, right? What are these 6 types of quarks? Up, down, top, bottom, strange, charm. Quarks are among the tiniest particles to exist. They are wonderful and mysterious, and we are still learning about them. They have some similarities. They have the same baryon number, the same spin, for example, but there are also differences. They have different charges, different flavors, different masses, different colors. They are different in strangeness, topness, bottomness, and charmness. But, and here we have the clincher, together, quarks, along with leptons, are the building blocks of matter. And guess what? Quarks cannot exist on their own. So what are the life lessons here? For one, together, as a people, with our similarities and differences, we are stronger. Together, we are better able to build a just and fair society. 2, we need each other, whether we realize it or not, to really be able to reach our potential. And I'm actually thinking of a song titled No Man is an Island, and it ends beautifully with each man as my brother, each man as my friend. 3, as tiny as you may think you are, as small as you may think your voice to be, you are not insignificant. You are of value. You are a building block in our society, and your contribution is invaluable in building communities that are life-affirming, that are diverse and just. Next, let's turn our attention now more to the macroscopic side of things. A stationary charged body produces an electric field in the space surrounding it. This means that if there's another charged body in that space, that charged body is going to experience an electric force on it due to the first charge. And because this second charged body is also producing an electric field, it too will exert an electric force on the first charged body. What about masses? Bodies with non-zero mass exert gravitational forces on each other. Life lesson: what we do affects the other. I affect you, you affect me. And by extension, how we choose to do it. Our actions can build persons up or tear them down. Let's then try to be mindful of how we treat each other, the things we say, the things we write and do. In closing, we are the quanta of our society. Let us do good and encourage others to do good. Let us respect each other and let us work with each other using our diverse talents and perspectives to build something great and wonderful. Thank you.
Thank you very much, Dr. Joseph, for your wonderful, creative, and inspiring life lessons physics edition. I can attest to learning some of these life lessons in my first year and was very inspired. The greatest sign of success for a teacher is to be able to say, the children are now working as if I did not exist. A quote from Maria Montessori. Our lecturers are in fact there to guide us until we have developed the necessary skills to do our independent work. For our next lecturer presentation, I would like to introduce Dr. Nikolai Zuzikov, who currently holds the post of lecturer in medical physics here at the department. Dr. Zuzikov received his Master's of Science in Radiation Biology at the Queen Mary University of London, and then his PhD at the Medical Radiological Research Center in Russia. His interest lies in cancer research, molecular biology, and cell biology, and he is also a well-published researcher. His most recent publication is the effect of 150 kilohertz EM radiation during folliculogenesis of PCO rachnoid. Join me in welcoming Dr. Nikolai Zuzikov. Over to you, Dr. Zuzikov.
Hey, good afternoon, colleagues. Good afternoon, students. I'm limited in time, so I cannot list everybody who is participation in this event. So what I'm going to do today, I'm going to introduce you to medical physics area. So let's start. So what is medical physics? You heard a lot about physics itself, and you probably know a lot about physics, but what is medical physics? According to term coming from Wikipedia, as well as from International Organization for Medical Physics website, medical physics is deal with application of physics knowledge for human health to make it better. So more about medical physics you can find in International Organization for Medical Physics website, but there is another international organization where you can find information about medical physics. Is International Atomic Energy Agency. Actually, I've got now a PhD students of mine who's got support from this agency. So what medical physics are using? We are using broad spectrum of electromagnetic radiation. I would say full spectrum. I was introduced with my paper, which is uses radio waves, but actually I'm radiation biologist and using other side of electromagnetic spectrum. So mostly X-rays and gamma rays, very energetic electromagnetic radiation. And medical physicists also use full spectrum of electromagnetic radiation, as well as full spectrum of different types of equipment, frequencies, and temperature. But you should know that all knowledge, including ionizing radiation, including physics knowledges, as sticks with two ends. So if you use one end, you will get a weapon which is used to destroy human, to kill people. So I hope you will not go to this side of stick, and you will go to another side, which is saving lives and used for diagnostic of different diseases. So in this slide, X-ray machine used for diagnostic of different diseases, not only for breaking of your bones, if it's happened accidentally, but to diagnose other disease is used. But you have to have a lot of knowledge, different knowledge to control and to use this machine. We now have these machines or such machines in many hospitals, almost in all hospitals, in laboratories. So we require a lot of medical physicists to work with that. But what would happen if you don't have enough knowledge? Working with such machines is shown here. So these slides came from one of my lectures and shown a quite good photograph of backbone on the left picture. And it's done with specific energy of X-rays. If you don't know which energy to use, you will get either central or right picture. So you will unnecessarily irradiate person, and you will not get image what would you like to have. So knowledge is very important, and without it, you will not be able to use complex, expensive, and smart equipment. So this photograph shows another modern equipment which called fluoroscope. And if you are unable to use it properly, you can continuously irradiate patient and produce radiation poisoning. You can even kill people if you don't know how to use this. Or you can destroy equipment. So again, you have to have a lot of knowledges. Another area of medical physics, in addition to diagnostic radiology, is nuclear medicine. For example, in the United States, tens of millions medical imaging and therapeutic procedures are performed each year, and now it's increasing as an exponent. Now it's about 100 millions per year. And nuclear medicine is quite safe and cost-effective and save lives if you use it properly, if you know how to use it. Another equipment, which called positron emission tomography, this is exact picture of tomographer, which supposed to come to new oncology center in Trinidad and Tobago. But who will control this equipment? Who will use this equipment? Of course, medical physicists. And what knowledge you should have to construct this device, to develop this device, knowledge of engineering, mathematics, physics, other knowledge is required to perform procedure. To perform scanning, you have to have knowledge of pharmacology, medicine, biology, physics again. So medical physicists got knowledge not only physics, but in medicine, in biology, of course in mathematics, a little bit in medicine. So multidisciplinary knowledge required to be medical physicist. But the main knowledge is a physics. For example, the previous scanner wouldn't be able to work without this cyclotron, which also supposed to come to your new oncology center. So how you can use and troubleshooting equipment like this, like cyclotron, if you don't have knowledge of physics. So it's very important to study, and study not trying to get A+ mark, but real knowledge. Another example where medical physicists are required is radiation therapy. There is National Radiotherapy Center in St. James in Trinidad, where medical physicists do planning in radiation therapy, and only medical physicists can do this. Of course, with assistance with medical doctors, but this is direct example where you can see that medical physicists save lives of people. And finally, if you are a medical physicist, you don't need to go to hospital or work with huge equipment. You can just go to research and help other medical physicists. I'm a radiation biologist, so I'm using ionizing radiation to see what's happened with living organisms, with cells. So what is presented in this picture on left top is normal bone marrow, how beautiful our cells look like. But what happens if you irradiate them, shown on the right bottom? You will not see cells, they disappeared. So another area which you can go in and apply knowledge of medical physics is research. So if you are not in medical physics yet, but you've got knowledge of physics, please come and join our classes. And how to do this, next presenter will report to you. Okay, thank you very much for your attention.
Please accept my deepest gratitude, Dr. Zuzikov, for your very informative presentation on the applications and importance of medical physics. William Butler Yeats once said, "Education is not the filling of a pail, but the lighting of a fire." Today, we hope that through our lecturer presentations, they can help ignite that fire for you with respect to physics, or at least fuel that which is already there. As we continue to hear from our very hardworking staff, I'd like to introduce a lecturer who is very enthusiastic to speak today. Dr. Roger Andrews is a lecturer in quantum physics and electromagnetism, as well as a coordinator for the MSc in biomedical physics here in the Department of Physics. He is a graduate of King's College London, where he obtained both his BSc and PhD with specializations in quantum physics. He is the recipient of many postgraduate and postdoctoral research awards and is well published in leading journals in physics. It gives me great pleasure to introduce Dr. Roger Andrews.
Right. Good afternoon, everyone. Are you all hearing me? Are you all hearing me?
Good afternoon. Yes, sir.
Okay, good. It's my pleasure to speak today, and I'm very thankful to the students of the physics department, and by extension, the students at the other campuses in Jamaica for organizing this event. I think it's the first event of this type that I have experienced since being in the Department of Physics for many, for more than 2 decades, right? What I would like, the question I would like to throw out to the students mainly, and everybody else who's online, is what ideas in physics do you all find most troubling? Very difficult to come to terms with, and baffling, almost counterintuitive. And I may throw out a couple of these. And on the first one, I would like to propose as very counterintuitive to our experiences in the classical world is that of wave-particle duality. You know, the fact that a particle, as we know it, can also exhibit wave-like properties, very, very counterintuitive. When does it behave like a particle? When does it behave like a wave? This is very, very mysterious. One idea I find very troubling as well, is the idea of electron spin. The fact that if it's a particle and it's a point-like particle, that it also has spin, but then it could behave as a wave as well. So these are very, very counterintuitive ideas that form the cornerstone of quantum theory and have applications. But today, following on from what Dr. Zuzikov spoke about, I would like to introduce you all to a career path with your physics degree that is growing, and it's very, very important in today's world. So let me share the screen here. Right, and it's our Master of Science in Biomedical Physics. Initially, we had a specialization in movement science and one primarily in medical physics, which is radiation-based. So currently, that's the only specialization we offer, but we do intend to increase the specializations as we move forward with this degree. Now, following from what Dr. Zuzikov was saying, we all know that medical physicists make a major contribution to the safe and effective diagnosis of treatment of patients, and their knowledge of physics, radiation physics, and their knowledge of the complex equipment which is used to interrogate patients and in modern diagnosis as well as treatment, and also their understanding of how radiation interacts with tissue and so on are all essential to the application of both ionizing and non-ionizing radiation. So some of the responsibilities that these medical physicists would have cover areas like dosimetry, treatment planning, quality control, equipment selection, radiation safety. In addition, imaging detectors, image processing, even radionuclides, coming back to nuclear physics, radionuclides and radiopharmaceutical production and use, all together with quality assurance and quality control. In addition, they commission, calibrate, and ensure the functionality of all this complex equipment in use in the hospitals. So this is a very timely talk in terms of the application of physics, because once we finish with our degree, we would want to find out, well, where do we go? And this is a possible avenue that you can explore. So we list there some of the career opportunities in academic and clinical research, biomedical engineering, clinical service, consultation, policy, drafting of policies for government and so on. Of course, quality control, very important, and medical instrumentation. So just to read there, the graduate has become a necessary requirement for advancement into research, development, supervisory and management positions. The field of biomedical physics is new and is constantly being redefined. More opportunities. You can even go into the PhD field. You can assist in the development of bionics, human movement, artificial limbs, artificial eyes, for example, as well. Use of knowledge in the curing of diseases, and you could contribute, of course, to quantum biology. That's an emerging field, neurobiology, and much more. Now, the entrance requirements for the master's degree is very moderate. These are the typical or traditional entrance requirements, but if you have a science degree and a willingness to transition into this field, the science degree that you have doesn't really matter that much, because we have had applicants being very successful and coming from a non-physics background. So I encourage all of you in the Faculty of Science and Technology at St. Augustine, as well as in Jamaica and Cayville and so on, everywhere in the Caribbean to apply. The degree is going to be run online, so there's no problem with you being physically here for 90% of the courses. So what are some of the courses we offer on this very important program? Well, as you can see there, we have physics of the human body, human anatomy and physiology, biomedical statistics and informatics. I mean, that biomedical informatics field deals with hospital management systems. It involves the use of computers and software. So even people from computer science can apply. They all have a space in this degree. Nuclear and atomic physics, very important. We do this at the undergraduate level as well. Numerical methods for biomedical applications, research methods, entrepreneurship, intellectual property. Some of the radiation physics courses there are there for you to see: radiation physics and dosimetry, radiation biology, oncology, biomedical imaging, workplace safety and protection. And we have 2 laboratory courses there as well. So basically, you want to apply for this type of master's degree, you can contact our administrative assistant, Mrs. Virginia Briggs, who's always very helpful to give students information. And we are willing to meet with you on a one-on-one basis in order to explain what this degree entails and in order to ensure that you make the right choice. So that's it from me today. And I want to thank you all again for being so enthusiastic about physics and for creating a community between the students and the lecturers, which is so important for the growth and progression of the field. So thank you very much.
Thank you, Dr. Andrews, for that presentation. We will share the list of programs as well on the council's page once again so that you all can see. I'm not sure if you would have seen Dr. Andrews if he was presenting. I think his connection was a bit poor. So thank you to all of our lecturers for your very fascinating presentations. We would now like to begin the question and answer segment for the lecturers for the next 10 minutes. So students and all other attendees, please feel free to send your questions in the live stream chat now. In the meantime, we do have some questions prepared to ask. So any lecturer that would like to respond, having to move to the online platform at the beginning of the pandemic, what are some challenges that you would have faced as a lecturer to keep your students' attention? And would you prefer the online platform or in-person classes? Any lecturer can answer. I'll call on a specific lecture just for sake. Dr. Hack.
Hi there, everybody. Okay, so do I want to teach face-to-face or online? I must say that online has exceeded any expectations I had up front. I have found it to be very effective. One thing I've seen a difference is that students actually communicate more with us online in terms of responding, asking questions than they would in the face-to-face environment. What I really miss, and I even said that in my presentation, is seeing your expressions, seeing if you're falling asleep, if you're rolling your eyes, and that kind of engagement. I really miss that. I mean, labs is a different thing. That one you really do need to be able to do hands-on. But that's it for me. I do love the online engagement, but I want to be able to see you all.
Thank you, Dr. Hack. Do we have any other responses from any lecturer?
Hello, this is
Hi.
Matthew here. Yes, I'm not a lecturer, sorry about that. But I'm coming from the MSc program in physics, biomedical physics. And what I can tell you firsthand, if you're considering a career choice, it's a good direction to go in. The program was taught out in such a way that it's not just learning in class, well, online now, but you actually get to go into the hospitals and you get to do quality assurance on the machines, right? In addition to that, I've noticed there is a growing demand for medical physicists in Trinidad. If you look around, you walk down the street, there's an imaging center almost on every corner. So career-wise, it is a good decision, right? That's it from my end.
Thank you, Matthew. So we do have some questions coming in on the live stream. So first question, what are some jobs in Trinidad and Tobago that are available with medical physics? So I believe either Dr. Zuzikov, Dr. Andrews, or Dr. Joseph can answer this question.
I'll take that question there. The jobs range from working at the National Oncology Center as a medical physicist, performing the various duties. You could work at the Mount Hope General Hospital, San Fernando General Hospital. You can work in the private sector as well. All the hospitals require the medical physicists to safeguard the operations of the equipment and to assist the medical doctors with the performance of their duties. So basically in any of one of the health institutions in the country, as well as in the region. A good thing about medical physics is that you're not just stuck with working in Trinidad. You can actually work anywhere where there's hospitals or health institutions. So you have a very transferable type of career, both in Trinidad as well as abroad. And also you have the professional bodies like CAMPEP, the IMO, the IAEA, which safeguard the degrees and the quality assurances and so on. So it's a very organized field and it's required everywhere. And it involves all the skills from the sciences, from computer science to chemistry and like in immunophenotyping and so on that you do in flow cytometry, which Dana will talk about. And all skills are involved in this very multidisciplinary type area whose basis is physics. And that's the important thing, that the basis is physics. Does that answer the question?
Yes,
Yes.
thank you.
Yeah.
So thank you very much, Dr. Andrew. So we have another question coming in. Does UWI partner with foreign universities in the area of medical physics or quantum physics, for example? So again, any of y'all can take it. I see Dr. Joseph is here. Dr. Sharma is here.
Anybody who wants to take that question, or you all want to hear from me once more? What about
That's fine, you can go ahead.
You go ahead, Dr. Andrews.
You sure? Well, we have been having the meetings with the IAEA, where they're trying to ensure that all degrees and so on are aligned with the ones there in Europe. Dr. Zuzikov has in fact been working on joint projects between UWI and the IAEA. So we are in fact forging these links with the international institutions, and we expect that we could transfer some students to work abroad, and then so that they could come back and then educate us here about what they found and the experiences and so on. The program was gate approved before the pandemic and so on, when the hardship started. And we expect that the program, once the government sort of balances off its finances, would come back and stabilize things so that they could bring the postgraduate programs again as with gate funding. So yes, we do have alignment with the international institutions, particularly the IAEA, and we have met the consultants from there.
To add, if I may, chairs, Ms. Paul and Ms. Bihari, I just want to add one bit there. We also have our graduate level students who, based on their program and their course of study, where they would require additional training and so on, they've been able to access training at institutions abroad. So that, and we've had that for students across the spectrum in terms of graduate studies, but also in the medical area and of course in pure physics, quantum physics as well, yes.
Thank you, Dr. Andrews and Dr. Joseph. Or Dr. Sharma, did you want to add?
Yeah, so
No
in
problem.
respect to the collaboration, so if you look at, we have MSc in renewable energy, okay, so we have collaboration in that program with the University of Flensburg, Germany. So we have collaboration in the program itself, and as far as research is concerned, every lecturer has a foreign collaboration. So we have academic collaboration as well as a research collaboration available in the department. Thank you.
Okay, thank you very much to all of our lecturers for attending and giving their presentations and answering the questions that were asked. We have now come to the end of the lecture presentations, and we know that your time is valuable and you are all very busy. So we deeply appreciate your support and your appearance here this afternoon.
Question time.
All right, so my next question, give me a moment here. Let me get my question really quickly. All right, so hold on, give me a moment. Right, so what is Einstein's most popular equation for energy?
5, 4, 3, 2, 1, go.
You know, I swore I saw that equation on a bag of sorts earlier today. So I'm wondering if anyone can recall that. All right, are we getting any answers?
Chat moderators, are we getting some
Yes.
answers?
Yes, we're getting some,
Okay, good.
And some correct ones too.
All right,
And some
great.
correct ones too.
Wonderful. Glad to see everybody's participating. So let's move on. So having graduated from Lakshmi Girls Hindu College in 2019, I would have spent most of my years looking up to the older students. And my co-host, Ms. Kyra Paul, was undoubtedly one of them. She excelled in Lakshmi Girls and continued to do so in university in her undergraduate studies. She's currently pursuing a BSc General with majors in mathematics and physics. She's the top year 1 performer in mathematics and physics, as well as the top 2 performer in physics major courses. Some of her hobbies include singing and learning the keyboard. Here to give us all some inspiration, let's welcome Ms. Kyra Paul.
Good afternoon again, everybody. Thank you, Amara. It is indeed a pleasure to be here and to be able to provide any sort of inspiration that I can. So to prepare for this, I've been asked to address a couple of questions. So I'll just tell you the question and then discuss it a bit. So the first question is, what is your favorite thing about your degree currently and your least favorite thing? So my degree consists of a double major in mathematics and physics. And my favorite thing would undoubtedly be how well they are interconnected. I'll be honest, I genuinely understand physics from a mathematical point of view. And conversely, via the various applications of physics, I have a deeper appreciation for mathematical methods. So that is for my actual degree. But specifically to physics, what I like is that there's a great importance given to research. And several of my courses here include research components that give students a bit of freedom to express and explore ideas which they are interested in. And one of those would have been my final year research project where I presented on quantum optical coherence tomography. And I not only worked in that field for a period, but I also was able to do research. So that was something, I appreciated. Regarding the least favorite thing, there aren't a lot of courses that can be used to transform my physics major into a physics special degree, which is what I actually wanted to pursue, an entire physics degree only. And so that's something that I say I would hope that can be improved. And then independent of my math major, I would also have liked to see more math courses within the physics aspect of my degree. Because as we all know, physics is no short of mathematical concepts. So just being honest, that would probably be that which I least like about my degree at the moment, the physics part of my degree. So the next question was, can you tell me about a time when you overcame an academic challenge? So I've had many academic challenges, and I think we all do at some point. However, in year 2, I was studying for a course called statistical physics, and I couldn't grasp anything in that part of the course, from microstates to understanding why they're even important. And Dr. Andrews was so right. Some part of physics like quantum mechanics and that wave concept, that was shaking me. And the microstates have a lot to do with the quantum nature of things. So I really couldn't understand or think about why that was important back then. And I got so frustrated that I decided to take a break. And I always recommend taking a break. And to get away from that, I did some craft. I listened to some music. And then when I sat down to do work, I just took my statistical physics book and put it aside. And for the rest of the afternoon, I spent time doing other courses that felt a bit more easy. And then finally, when I calmed down, when I was able to do things that, what didn't make me so frustrated, I returned back to statistical physics. And lo and behold, when I did, I was more calm, and I really sat down and became open-minded to all of the information that was there. And definitely I didn't have an easy time. It was still hard, but I was not as frustrated as I was before. So sometimes taking time away from something that challenges you and to the point of frustration can really help you look at it from a different perspective, a different angle when you return. So the third question I was asked is, what extracurricular activities do you engage in outside of school? So it is very important to not just study all the time, but to pursue extracurricular activities that help you to relax, de-stress, and then take a break from these devices that we are bound to at the moment. I do quite a bit of things. I take keyboard classes. I am currently trained to be a yoga instructor. I coordinate religious programs in my temple. And I am a member of an organization called the Hindu Swayamsevak Sangh, where I attend weekly meetings with youths, where we play games and have thought-provoking discussions, etc. And all of these activities help me to build skills that I would not have gotten by just being a student. And I would have also used these skills to improve on the type of student that I am. So I would really like to encourage all of you to really think of pursuing something that's extracurricular, that is outside the realm of school or your degree. The last question is, how do you cope with being in the pandemic and having to study for school as well as do your assignments and exams? So at the beginning, I really struggled to maintain a balance, and I'm not a master at it. It's still very difficult. But the idea that I follow is that to set certain times where I do serious work, I'm very focused. And then other times where I take a break and then maybe do something fun, like play with my dogs or play music or just walk around. And you will see that as the semester progresses, it does get tougher because you're going to have a lot more exams and assignments, and time management really plays an important role. So when you have predetermined time to do certain things, it really helps you to appreciate the time to study as opposed to your time to relax. So that's something that kept me going, and it's not something I have completely mastered, but it's something that I'm trying to be better at. And then the last question is, what are your plans for your future after this degree? So this is going to be very short because I definitely know I want to pursue postgraduate studies. In what, I am not sure. Ideally, I would like to build a foundation in theoretical and mathematical physics, so like maybe some Masters of Science program around it. But I'm definitely unsure as to which field of physics I would like to venture in. And in the last thing I have to say, my advice would be for anyone listening, not to rush in making a choice on what you want to pursue. Definitely research on the requirements for the fields that you are interested in and ensure that you are convinced that is where you want to invest your postgraduate years into. So as I conclude, I would just like to thank FSTSC for this opportunity to not only host, but to give this short inspiration message. And I thank you all very much for allowing me to do this. So as we move on in the program, as you know, inspiration can come from many sources, and it's a different feeling, however, when you can become inspired by your own peers. I'd like to introduce Miss Dana Boodoo, who is one of my peers and a past graduate of Bishop Anstey High School and is currently pursuing a BSc General with majors in physics and a minor in medical physics and bioengineering. Her hard work and dedication has led her to being the recipient of the UE Star Scholarship, excuse me, as well as academic prizes for the best performer in the courses bioengineering, and medical physics. Unfortunately, she could not join us live today. Oh, my voice is going. But due to electricity issues, she has pre-recorded a presentation for us all. So I would invite you to take a look at that.
I do see that Dana's actually here. Dana, would you like to do the presentation live, or do you want me to share the recording?
In the interest of keeping in the time frame, it probably would be safest to share the recording.
Okay, no problem. No problem.
Good afternoon, everyone. I'm grateful for the opportunity to present today. As was said before, my name is Dana Madeline Boodoo, and my final year project is on light scattering and leukemia diagnosis using flow cytometry. So let's begin with a couple concepts. Leukemia is a disease generated by the proliferation of mutated cells of the blood and bone marrow, and it can be subdivided depending on the duration of the disease and the type of cell affected. Diagnosis precedes treatment, which leads us to flow cytometry. This is the process of passing cells in a fluid phase through a narrow passageway created by laminar flow of sheath fluid so that cells can pass in single file to be exposed to a laser. Fluorescence and light scatter are hence analyzed, and the image demonstrates a schematic of the device. Also, me-scattering of light from interaction with cells is seen, and it possesses directional powered scattered lobes, usually with particles whose diameter is comparable to the wavelength of light used. To build to the light scatter of a cell, I first considered a simple system of spherical coordinates with a particle at the center. These are the resulting equations for incident, internal, and scattered fields from Maxwell's equations according to Bohren and Hoffman. The scattered lobe formation is related to these angle-dependent functions. As the order increases, the pattern is generally that the lobes created increase. Just to add, here are some examples of Mueller matrices for some of the components, such as the photomultiplier tubes in the flow cytometer, that evaluate the depolarization of light through cells. The light scattering profiles on your right analyze the light scattered from cells. Now, analysis using Maxwell's equations for numerous cells can prove to be quite tedious in realistic scenarios. So to overcome this challenge, the finite difference time domain method can be used as it accommodates analysis of scatter from biological cells that are not ideally spherical or homogeneous. The software used in the experiment was ANSYS Numerical, which is commonly used for photonic simulations. They provided a sample file catered to me scatter of whose parameters I augmented to simulate a white blood cell, which was one of my aims for the experiment. Here's the basic layout of the simulation, and this is a brief overview of my method. I firstly simulated a single sphere in air with a diameter of 7.6 microns and refractive index of 1.37 to match that of a lymphocyte. This is the type of light scatter that resulted, and in flow cytometry, this would be characterized as side scatter. However, this initial structure did not accurately reflect the lymphocytes that would be analyzed in this field due to failure to integrate three main parameters: the presence of a nucleus, the non-spherical nature of the lymphocyte, and the granularity of the cytoplasm. Attempted amendment was made to include the first parameter within the bounds of the program. Given that lymphocytes have nuclei, an additional sphere of radius 1.5 microns and refractive index 1.338 was added to the existing sphere. I further experimented with the placement of the nucleus. Nuclei within cells are not centered as a rule, so I offset the central nucleus to 111. Here, the radiation far-field plot produced the most significant visualization of how the light was scattered. The expected significant forward scatter and little back scatter of the light was seen as compared to the sphere with the center nucleus. This is a video demonstrating how light propagates through the structure that I created. The limitation of granularity and non-spherical nature of the cell remained unrectified, however, which perhaps warrants the need for further investigation of the program functions and the intervention of alternate software in future study. Despite this, ANSYS Numerical was still able to achieve the basic demonstration of the forward scatter of light. I then investigated the diameter ranges of leukocytes in normal patients and those having chronic lymphocytic leukemia. The range of diameter of 5 to 11 microns as compared to 4.5 to 10 microns demonstrated that in cases of leukemia, diagnosis by light scatter alone in flow cytometry poses a challenge. Given this, the identification of proteins must be applied as a means of subdivision. Due to the limitation of not having access to a flow cytometer, the flow cytometer dual plots for lymphocytes were researched. The first image shows the gating of a population of lymphocytes that is further differentiated using a fluorescent dye, which is called fluorescent isothiocyanate. And CD3 and CD19 markers were used to distinguish the T and B cells. The second image here shows the expressions of CD19 versus CD20 in a population of cells in a case of acute leukemia. The red region demonstrates neoplastic populations, that is, the accumulation of tumor cells. Yellow regions display T lymphocytes. Green regions display maturing granulocytes, and blue regions signify B lymphocytes. Simply demonstrates the CD markers, which are protein expressions. These specific markers, common to leukocytes, identify certain leukemias, and markers such as CD56 can indicate the severity of the disease. So flow cytometry does not just identify the disease, but it also reveals information about its progression. I also researched data collected on Trinidad and Tobago. However, such literature was limited, and the most recent article I was able to find quoted results from 2001 to 2006. There were 145 new cases of cancer in the age group of 0 to 14 years between this time, 56.6% of which were males and 43.4% of which were females. The major types of cancer diagnosed in this age group were leukemia at 40% and tumors of the central nervous system at 18.6%. I also researched the treatments for leukemia in Trinidad and Tobago. Though literature also proved limiting, I found a paper that highlighted treatment for chronic myeloid leukemia, specifically imatinib mesylate, IM. Most common side effects of this treatment were skin hypopigmentation, cramps, and weight gain. They were recorded to be less severe than those of interferon treatment. IM employs tyrosine kinase inhibitor and is efficient in the eradication of the Philadelphia chromosome to control proliferation. However, it was also stated that the treatment would have proved more effective had there been earlier diagnosis. I also researched the usage of a flow cytometer in Trinidad and Tobago. A paper by Kulhade et al. In 2017 indicated that a flow cytometer was used to obtain results on investigated interleukin-6 among subjects in Trinidad and Tobago. However, it was not explicitly stated in the report if this device was located within the country or if flow cytometric analysis was outsourced and conducted overseas. Given the limited literature on its usage, this could suggest that insufficient research has been conducted on the impact of the flow cytometer within the diagnostic medical field in Trinidad and Tobago. So a flow cytometer can help in improving the efficiency of leukemia treatment. Early identification using the device can accelerate and improve the treatment process to mitigate its proliferation. At present, a flow cytometer may perhaps prove useful in identifying COVID-19 from its fluorescence-activated cell sorting. The distinct fluorescence of an infected cell can aid in diagnosis of the virus. And that's the end of my presentation, and I thank you for listening.
Thank you, Dana, for that wonderful presentation. I know we would have wanted you to do it live. We weren't aware that you would have had current at this time, but thank you once again.
I'm glad I was able to make it.
Thank you. So you'd be present a little bit later so that whoever asks questions, they can direct their questions to you. All right, so Mr. Brandon Rajkumar is a recent MPhil graduate from the Department of Physics. His MPhil research focused on the use of fractal dimensions to analyze sunspots and their magnetic fields to better understand their underlying complexity. He's a founding member and vice president of UE Stargazers. He enjoys sharing his passion for astronomy and physics with those around him. Currently applying to PhD programs with the hope of continuing his career in astronomy and physics. So I'll now share his recording with you all.
Hello everyone, my name is Brandon Rajkumar. Happy Physics Day 2022. And I just graduated from the Department of Physics at the University of the West Indies St. Augustine campus with an MPhil in Physics with a focus on solar astronomy. Today I'm here just to share my appreciation for physics and to answer a couple of questions that was given to me and share a little bit about my journey, my experience with you guys. So why did I choose physics for all fields? The truth is I didn't exactly choose physics. Physics kind of chose me. When I applied to university, based on the advice that I received, I wasn't really sure what I wanted to do. And I chose a bunch of engineering options, engineering programs. Luckily, the university saw it fit to put me in physics and math. And in my first year, I had the wonderful experience to meet with some lecturers that really showed me how interesting physics can be and how physics is all around us. And that really clicked with me because I was always curious about how things work. And learning physics allowed me to understand how particular things worked. In my second semester in my year one program, I found an outlet for my passion for astronomy, and everything just kind of clicked, and I've stuck with physics ever since. So what made me decide to pursue postgraduate studies having completed my first degree? To be honest, it was an easy choice for me. I've always been interested in doing research, working with my hands and trying to understand things. So when I got the opportunity to really, like I said, explore my interest in astronomy, I really jumped at it, grabbed at it. And I knew I wanted to reach here eventually. And these are the these are the options I had and the paths that I would take to get there. And postgraduate postgraduate studies was just one of those paths that I decided to take. So based on my experience in undergraduate and now postgraduate studies, what is one of my most favorite memories or parts of either of my degrees thus far? For me, my favorite thing about both my programs was the opportunities that I got to do things outside of like traditional academic studies. So the opportunities I got to work with telescopes, to collaborate with professors from around the world, to meet and interact with people from different places, and to even visit some of those places. Those were the best parts of my programs for me. The things that I learned during those interactions, during those experiences, in my opinion, outweigh the things I would have learned in the classroom. And I'm so appreciative for those opportunities because not everyone gets to have those types of experiences. What was the most challenging part of my first degree and what kept me motivated during those difficult moments? For me, the most difficult part, the most challenging part was final exams. I would love to interact in the classroom, but when it came to exams, I always drew to a blank. So that was the most difficult part for me. However, in my second and third year, I did develop techniques to kind of help me with studying, and that made those final exams a lot less challenging, a lot less intimidating, and I think that helped. Luckily, in my current research program, well, the MPhil that I didn't have as many exams to take, so that was wonderful. Is all the stress what motivated me during those difficult moments? So again, because I knew exactly what it was I wanted to do eventually, I always had this goal that I had for myself, and this allowed me to stay motivated during those hard times. I knew this was just a part that I would have to take in order to achieve the goal that I really eventually wanted for myself. So I was okay doing this. Is all the stress of university worth what comes after students graduate? In a nutshell, yes, I definitely think it is worth it. I think university is more than just the stress. You get all these different experiences outside of the classroom that are valuable to you as a person. The experiences you gain by interacting with your lecturers, with your classmates, by doing things or having opportunities that you wouldn't normally have in this university setting, I think helps you become a more well-rounded person, and I think that is definitely worth the experience, even the final exams. So with that, I'd like to say thank you for taking time to listen to me, and again, happy Physics Day, and just keep wondering about things. I think you'll find a passion for physics, even if it's not something that you want to study.
Okay, thank you, Mr. Rajkumar, for that wonderful video. After listening to that, it's very encouraging knowing he was one of my demonstrators for my year 1 physics labs. And although it's very intimidating to reach out to your demonstrators and your lecturers in your early years, it's reassuring to know that they're here to support you in your degree. So if you ever feel the need, you have to reach out to them. And they're very friendly when you do. The next presentation we have is from Miss Jemmy Greasley. She's a Trinidadian-born physics enthusiast who recently began working as an AP at the Department of Physics with Dr. Andrews, as well as the Department of Computing and IT under Professor Patrick Hussain. At FST, she carries out her research work, supports various other projects, and is assisting with laboratory teaching in a couple undergraduate and postgraduate courses. She attended St. Joseph's Convent, Port of Spain, and graduated in 2013 with 10 distinctions at Cape A levels, which led her to obtain a National Open Scholarship in Science. She speaks French fluently and decided to pursue a BSc in Physics at the University of Paris, the Sorbonne University, which is the fourth oldest university. She returned home in 2017 and recently completed her MSc in biomedical physics at the University of West Indies. Her MSc thesis was on crystallographic analysis of kidney stones with X-ray diffraction analysis and electron microscopy. Her first paper on this work was recently published at the Journal of Applied Crystallography. Despite her interest in medical physics, her passion lies in quantum science. Following her master's, she returned to this discovery of quantum computing and quantum machine learning and hopes to pursue her PhD in quantum algorithms development for solving problems in crystallography, condensed matter and physics, and material science. So I'll now share her recorded video.
Hi everyone, my name is Jemmy and I'm so happy to be able to give this talk at FST's first ever Physics Day. Firstly, I'd like to thank the persons responsible for putting together the event because I think it's so important to talk about physics and its impact in our world, in our society, in our lives. So I'm very grateful for this opportunity to discuss, of course, my personal history and passion for physics and why I think it's so central and relevant to the modern world. You may or may not know me or have seen me around in pre-COVID times, depending on whether you are an undergrad or postgrad. But just to cover the basics, I was enrolled in the MSc Medical Physics program and completed it just last year. But a couple of you may also know me from when I demonstrated for Year 1 labs back in 2019. Also, recently I've begun working as an AP in physics and DCIT, where I do research in crystallography, machine learning, quantum computing, and quantum programming. And yes, that sounds like a mouthful. So exactly how did I get here? Well, yes, of course, I chose to study physics at university, but before that, actually way before that, I had already set up myself on this path, or rather I'd like to think that this path chose me. I remember I must have been 7 or 8 years old and I was reading a science book, a kid's science book, and that's where I first learned about this idea of something called an atom. I know as children and naturally curious, a lot of us are fascinated by things like the stars, the moon, the planets, and the sky, but somehow I was so pulled by the fact that everything around us was made up of these so-called building blocks that was so tiny that you really couldn't see them. And then I thought, well, okay, what exactly were those essential or fundamental building blocks made up of? They must be made up of something. And so I could have accepted that things get bigger and bigger, you know, like to form the stars and stuff like that, and our entire planet, like things grow in size, but somehow I wanted to know what happened when we zoomed into the extremely small, like past the size of the atom. What itself was the atom made up of? And then what about the things that made up the atom? What were they made up of? Etc, etc. And so I wanted to very much understand this whole atom thing and expected that when I reached secondary school I'd get an answer, but of course things got more confusing and the definition of what it was changed completely between Form 1 and Form 6, especially like how it looked like, the pictures that they gave us. In any case, by Form 3 I knew I wanted to become a physicist, and in Form 4 I was so settled on doing particle physics, and I would kind of imagine myself as this cool hip lady scientist working at CERN at the LHC. So the thing is, I couldn't help but love physics, and I had more questions on physics than I had on any of the other sciences that I studied. And of course, the more in depth that I learned going through school and university, the more I came to understand some things, of course, and at the same time the less I understood like everything else. Right? And it kind of became a rabbit hole scenario, but I'm kind of committed to the rabbit hole now, so it's quite okay at this point. Though I'm not right now aiming to venture into particle physics anytime soon, or even continue much longer in medical physics, which is what I did for my master's. I am so happy that I chose to follow my curiosity, and that even though there were moments of uncertainty during my time as a student, like where I didn't know what was the next step or where I wanted to study next, or if I'd even make a good scientist, everything sort of figured itself out with time and patience and persistence. And I stayed true to my passion, and I now get to prove to myself every day that I can be really good at this thing, you know, that I can continue learning and growing, even despite my doubts at times. So doing physics was sort of inevitable for me, even though a lot of people question what I do once I'd finished studying, and how would it be able to get me a job. And to answer that, I would say that a lot of people aren't aware how relevant physics is to the modern world and how we live. You know, the technology we use, our computers, phones, television, the internet, Wi-Fi, noise-canceling earphones so that we can listen to our music, enjoy our movies, you know, fluorescent lighting, you know, the fact that we have electricity in our houses, and, you know, cars, modern transportation, airplanes, trains, medical technology, equipment for testing. You know, all of these things operate on the principles of physics. Someone had to take the time to observe and understand nature, materials, energy and forces, to try to explain these things so that we'd be able to apply it in new and interesting ways. And we're not done yet, because physics today is more exciting than ever. There's so much left to learn, as science itself is a process of continued discovery, of renewing good ideas and erasing old ones, and correcting our thoughts and our theories based on the new observations that we make in experiments. It's about increasing our body of knowledge, our body of understanding, and making good use of these concepts by engineering new solutions to society's problems. So the advice I'd like to give to you guys today, whether you're now starting off in your program or near the end of it, or whether you pursue a career in academia, research, industry, business, entrepreneurship, or in education, is to give in to the idea that your education literally never ends, and that you should never want to stop learning, never stop discovering and rediscovering things, even with many challenges that you have to face. Enjoy every step along the way, and especially enjoy being a student, even when you have no idea what comes next. Right? And maybe you'll discover for yourself, like I did, that physics isn't just something that you study during your time at university, but it's something that you study for a lifetime. And so to end off, I have two quotes for you, and the first one is this. It says, "Physics is the science of all the tremendously powerful invisibilities of magnetism, electricity, gravity, light, sound, cosmic rays. Physics is the science of the mysteries of the universe. How can anyone think it dull?" And the second one by Marie Curie is, "Nothing in life is to be feared, it is only to be understood. Now is the time so that we may fear less." Okay, that's it. So thank you guys for listening to me today. Bye.
Thank you to the undergraduate and postgraduate students. We truly appreciate all the input that we have received this afternoon. And we all know that inspiration from undergraduate and postgrad students, the undergraduates who are currently excelling in their studies and the postgraduate students who have successfully graduated, it is all invaluable experience to all of us. So thank you, and I pass you over to Amara.
Yes, no problem. So if there are any questions for Ms. Paul, Ms. Guru, Ms. Creasley, and or Mr. Rajkumar, please feel free to send them in the chat now. In the meantime, do we have any questions for Ms. Paul, Ms. Guru, Ms. Creasley, or Mr. Rajkumar from any of the lecturers here?
What about the flow cytometry?
Mm-hmm. We'll just wait on our chat moderators to let us know if there are any questions coming in on the live stream. No questions yet. I believe what we would have done as the committee, we would have done questions for the undergraduate and postgraduate students to answer. So I think if there are any other questions, we can address it later on in the program. So we'll move on for now. So we have one question. Other than physics, do we do math as well?
Who wants to take that question? I think either Brandon or Carol could take that question.
So yeah, I'll take the first one. So I do math as well. I'm currently pursuing a major in math. So I would have done courses in linear algebra, abstract algebra, probability, and calculus, all of which I have used in my physics part of my degree, and very, very interesting concepts when you see how they merge together.
So I'm seeing another question here for the postgrad students. Let's get the chat. Right, I see a question here about what do you think is the most difficult physics concepts? Who wants to answer that?
Hi, hello. I can answer for me first. For me, I think probably string theory or anything in quantum is probably the most difficult things to grasp right now, because we just haven't figured it out completely yet. It's still all new and it's kind of at the forefront. So there's a lot of new things to be discovered and so much that we don't quite understand about it yet. So I think those are probably the more difficult concepts to understand these days.
Okay, thank you, Mr. Rajkumar. One more question.
I could also kind of answer that question, which is essentially, yes, interpreting quantum mechanics, because even the quantum mechanics is something that is like 100 years old now. Yeah, about 100 years old, right? It's still difficult trying to answer what it all means or how should we interpret it. So yes, there are many theories on how to interpret quantum mechanics. There's many thoughts behind it. And the question is, will we ever know? Because some things may be beyond that which we could touch with experiment. And it kind of goes a lot with string theory as well. As Mr. Rajkumar says, you know, a lot of these things may not be ever able to be tested via experiment. So, you know, we might end up, you know, just, you know, so whether we will know or we won't know, that is a question. But one thing we can do for sure is, even though if we don't know how to make sense of it all in the philosophical light, we can still use it to our advantage and use quantum technologies and yes, and apply it, right? Okay, that's it.
Wonderful. Thank you, Ms. Greasley. We have one more question, two more questions actually. Are the Marvel movies with quantum physics accurate with their physics representation?
I think Brandon could answer that since he's
Yeah. So I'm a big Marvel fan. I'm quite up to date with all the Marvel movies, everything on Disney Plus and all the other subsidiaries of it. So while the Marvel Cinematic Universe, they try to incorporate as much real physics as possible, a lot of it is fiction. Some of the ideas and theories that they use in their explanation is based on real theories that have been presented. So the multiverse theory is a real theory that has been presented. But of course, the extent to which they explain it, a lot of fiction, they take a lot of liberties with it. So it's not completely accurate.
Thank you, Mr. Rajkumar. We see Dr. Zuzikov, Marvel got advanced idea of physics fantasy. Yeah, so okay, so there was one more question that I had in the chat. What was your favorite part of research? I guess what's your favorite part of doing research? This can be directed to any of these students. So who would like to take this question? I think Dana can answer this one because Brandon and Kara did. Dana, are you here with us?
Looking back on research, first, before I say what was my favorite part, I have to also say that my preconceived notions about what how difficult it can be when my favorite part about it is when something does work. There's a different oh, my internet connection is unstable. Okay. But I think my favorite part about it is when something does work. For my project, when I had to simulate the white blood cell, I still knew that there were so many things that I could think of that I could have added to my simulation, and time is running out and things were just not working. And on the exact last day that we were supposed to present on our results, that's when something worked. And I think that moment is usually, it really is the favorite part, because you realize that, hey, just like Thomas Edison, who failed at making the light bulb so many times, I think he's definitely one of my favorite scientists, by the way. When you see that something you've been trying works, that has to be the best part, because it almost validates the struggles that you've had coming to the point of being able to solve your problem. So that would be my answer.
Thank you, Dana. Okay, so I think that brings us to the end of the question and answer segment for our undergraduate and postgraduate students. I want to say thank you once again to both undergraduate students, Ms. Paul and Ms. Buru, as well as our postgraduate students, Mr. Rajkumar and Ms. Greasley, for your interest in the event and your recordings and doing your presentations live. It's very helpful to hear from students who are currently pursuing their studies and have already finished one degree, for the students to currently hear that, you know, you can be successful, you can get through this degree, and you can do it being happy. So now we have question time. Read next question.
So my question is, light can behave as a, finish the sentence. So light can behave as a, I believe one lecturer went over this already. So let's see if
Yes,
someone can,
I remember.
can remember.
5, 4, 3, 2, 1, go. I know that there's a delete, so we'll give them a few seconds to type out an answer. Light can behave as a All right, so we have some answers coming in, so our chat moderators will note them down. So now we enter our club presentations. So to start us off, I would like to reintroduce Mr. Oren Green of JAMSPARC. As previously mentioned, he's the president of our sister club at the Mona campus, and his presentation today focuses on the artificial sun. How interesting. I hand over to you, Mr. Green.
So hello, everyone. Again, greetings from Jamaica and greetings to our sister club there in Trinidad. I would also like to just welcome you all again. Happy Physics Day 2022. So we're going to be looking at something that has encapsulates a lot of the sensationalism of journalism and physics and how they relate to each other. So the artificial sun and humanity's energy crisis. So as we spoke about before, physics is boundless. And physics is so boundless that when people heard of this artificial sun being launched into the sky per se, they quickly believed it. And I would have said to myself, you know, deductive reasoning would have told me that this might be misinformation, but a lot of people believed it outright because they know of the power and the limitless potential of physics, right? So we'll be going into that today and what the artificial sun really is. So the presentation outline will be going into, we are in an energy crisis, the issues with current alternatives, why an artificial sun and not like an artificial moon, and what China's breakthrough means for us and this energy crisis. So we are in an energy crisis. So Thomas Edison said once, we are like tenant farmers, chopping down the fence around our houses for fuel when we should be using the nature's inexhaustible sources of energy, the sun, wind, and tide. And he hoped that we wouldn't reach the point where we're almost out of the said fuel before we start turning to these alternatives. And you know, so said, so done. We're at this stage where we're in a crisis. We have little time to find an alternative that can meet all of our energy requirements and needs. And for the energy viable fossil fuels that we have currently, some of them only can last for a couple lifetimes, right? Or a lifetime essentially. So for coal, we only have 150 years until that's depleted. Uranium 90 years, natural gas 50, and oil 50. Right? So we're kind of in troublesome times here. But if I've learned anything over my tenure as a physics student, I know that science and physics can solve any problem. It has done it once, it has done it twice, it has done it many times, and it will do it again. So what will happen if we don't find an alternative? Essentially, we'll go back to the days where we won't be utilizing electricity. So we won't have internet. We won't have phone and power lines. We'll be back to using candlelight, stuff like that. And it is very concerning because the projections that I spoke about before, right, they do not include the countries, the developing countries around the world, which are just building infrastructure to utilize these fossil fuels. So we might have even less time than we thought we had, right? So it's very important that we figure something out. But so far we have come up with a few alternatives. One of which being wind power. Wind power has shown a very good potential to generate energy and to do so in a good amount of time. But the issues with wind power kind of bring back the sensationalized view of wind power and solar power and hydropower being the way to go. In that a lot of them need constant wind to constantly generate energy, and that just is not the case because air movement air moves in currents, and very high winds and storms can damage them. And if they are broken or destroyed during natural disasters where high winds usually reside, they can fly off and damage nearby property, eliminate human life, and could even be disastrous for flying animals. They are expensive and they are fairly loud. You could imagine something the size of a ship essentially swifting through the air consistently. It would be very loud as it displaces the air and causes refractions and compressions to make sound. And they take up a lot of land. So what about hydropower? Could hydropower work? Let's see. In most cases, hydropower is a very good alternative. The only issue is that it drastically changes the landscape and it causes, and the rivers around it. So it causes rivers to reduce flow and it causes water temperature to raise because water is in constant movement, aka kinetic energy. And it also degrades water quality due to sediment buildup because as water interacts with the sides of the dams, essentially degrades it over time, causing sedimentation. And that can pose a threat to wildlife and aquatic life. So what about solar power? Our piece de resistance. The sun powers gives life to everything on this planet. I'm sorry, I'm hearing background noise. I don't know if, okay, right. So the sun gives life to everything on this planet. We can give our thanks to the sun for all of the energy that we utilize to live and breathe today. So if we can find another way to get the power from the sun, that would be great, right? The only issue is that the way how we harness the sun's power right now is by utilizing toxic rare materials in order to build photovoltaic systems. And that has indirect consequences on the environment. Sun power also has the intermittency issue where if the sun is continuously shining on the photovoltaic cells, they won't generate current and they won't generate energy. But this could all be solved if we could just store energy for later. Well, unfortunately, we're not there yet, and we need to get somewhere fast because we are in a crisis, right? So storing solar energy right now is very expensive. Scientists in China are really trying to look into ways to do this, but so far we haven't found much leeway, right? So what do we turn to? We turn to essential fusion power, which is different from fission power, right? So fission is you would notably know it from nuclear reactors of the past, but fusion is different. So let's hear Korkuzart explain to us what fusion energy is and what it's really about.
The fundamental currency of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways, burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot, millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we wanted to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place. These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe. The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology. And although they can achieve fusion, right now it costs more energy to do the experiments than they produce in fusion. The technology has a long way to go before it's commercially viable, and maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth. But if it gets there, it would be so efficient that a single glass of seawater could be used to produce as much energy as burning a barrel of oil with no waste to speak of. This is because fusion reactors would use hydrogen or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads, which makes it incredibly expensive. So we may need another fusion buddy for deuterium instead of tritium. Helium-3, an isotope of helium, might be a great substitute. Unfortunately, it's also incredibly rare on Earth. But here, the moon might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the moon. Instead of making helium-3, we can mine it. If we could sift the lunar dust for helium, we'd have enough fuel to power the entire world for thousands of years. One more argument for establishing a moon base, if you weren't convinced already. Okay, maybe you think building a mini-sun still sounds kind of dangerous. But they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically. If the confinement failed, then the plasma would expand and cool, and the reaction would stop. Put simply, it's not a bomb. The release of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment. Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted. So we've just told you that there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So, what's the catch? Cost. We simply don't know if fusion power will ever be commercially viable. Even if they work, they might be too expensive to ever build. The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses. Or maybe, when the payoff is unlimited clean energy for everyone, it might be worth the risk. Videos like this one take hundreds of hours to make and are made possible by your...
So as we can see, one of the many things about physics and about science in general is that we try to predict what is going to happen utilizing theory. But things can be a bit tricky when we translate them to reality, right? Here we see that although fusion power has great potential and great advantages if proven viable, it still has the drawbacks of, not having enough of the specific resource and stuff like that. But however, if we invest time into it and actually see where it goes, it could be viable and could be the answer to the crisis and the debacle that we're having right now. Give me a moment here. All right. So we know that China recently had a breakthrough with their artificial sun. And a lot of you might be asking, wait, if the artificial sun is in a reactor, what did I see? That video that I saw on WhatsApp, on Facebook, of something ascending into the atmosphere, what was that? So have we done it? Did China's artificial sun really launch into the sky? Are we really safe from the energy debacle? Well, not quite. As you can see here, we're gonna go over the video that we saw before.
Of what looks like a ball of light and gas went viral, with users claiming China had actually launched its recent experiment into the sky. One video, which has been retweeted over 20,000 times, pictures a bright light ascending into the air followed by billows of smoke, with a crowd of onlookers on the beach avidly capturing the moment on their phones. The posts have since been debunked, as they reportedly picture a completely different event, the launch of a Chinese rocket a few weeks prior. Snopes reports that the video is likely to be from a launch from Wenchang Space Launch Center in Wenchang, Hainan, China. Another viral video, captioned the moment China launched the artificial sun, as night turned into day, shows a similar ball of light, with its ascension taking place at night. Twitter users commented on the event, with many frightened by the possibility of a fake sun. China's actual...
Right, so as we were saying before, a lot of people are under the impression that scientists today, our main goal is to replace everything with an artificial version. And that is not the case, because if something is working naturally, there will be no need to replace it, right? Not everything that we can do, we should do or will do, right? So it's not a case that, oh, scientists are trying to replace the sun and so are trying to inadvertently change the way how the natural processes of reality and the universe work. Nothing of the sort. That's preposterous, right? We want as scientists nothing but to improve the human condition and to improve the world around us. Because as at one point on this planet, humans did not exist. If we do not exist, it will not do any irreparable damage to the world. So we are responsible for sustaining ourselves. So if we run out of energy, it's on us to figure out another way to have energy, right? Our survival is dependent on us. If we go extinct, that's just it. There's no cosmic entity or being is going to stop everything and say, let's start over. We're just gonna go away. So we have to figure out these things for ourselves. But now that we know that that ball of light that flew into the sky was just a rocket, why are people so quick to think that, you know, an artificial sun was made and launched? It has to do a lot with the sensationalism in media and in journalism, but it also has to do with the distrust that science has somehow accumulated over time with the common man and the layman, right? And it is our responsibility as human beings, as fellow stewards, as good people, and as scientists to make sure that everyone has some sort of scientific literacy so they will not be easily led astray and misguided in such ways, right? So they can have the cognitive ability to make the dissonance between what is true and what is misinformation, and so that it will not cause them to have panic attacks essentially about, you know, the world changing around them and leaving them behind, right? So it's very important to understand the societal perspective of science and physics itself and how that relates to investment and industry. Because if people believe that something is very dangerous, they will not want their tax dollars to go towards it. A majority of the funding that goes into these big kind of very wow, eye-opening experiments come from tax funding. So it's very important to understand the relationship. So let's dive in truly to what China's nuclear fusion reactor actually did. What was so special about it? If it didn't actually fly into the sky, what is all of this commotion about?
Nuclear fusion breakthroughs have been coming thick and fast in the past few months. Here's the latest one. China's $1 trillion experimental advanced superconducting tokamak fusion reactor has superheated a loop of plasma to 70 million degrees Celsius, or 5 times hotter than the sun, for a new record of just over 17 minutes, according to Live Science, breaking the previous record of 390 seconds set by France's Tour Supra Tokamak in 2003. Nuclear fusion involves using extremely high pressures and temperatures to induce collisions between hydrogen atoms to make helium, which sees matter converted into light and heat. This process is at the heart of how stars are fueled, and mimicking it is extremely desirable because it does not generate greenhouse gases or nuclear waste. One key difficulty, though, is that fusion reactors cannot recreate the same intense pressure for the reactions as stars, and thus must operate at much higher temperatures. Controlling plasma at these temperatures so it doesn't burn through reactor walls either with lasers or magnetic fields is extremely problematic technically, and as such, New Atlas clarifies that rather than fusion, the latest experiment tested the Chinese tokamak's ability to tolerate such high temperatures over long periods, sustaining superheated plasma similar to the kind that will eventually be used to create fusion, but for now generating much less energy output than goes into it.
As you can see, China's breakthrough was something to behold, something truly to admire and to, you know, have awe in, and to be very Sorry, there's a lot of noise going on. Hopeful about, but still, we're not at the. As said before, the journey in physics has just started. We are nowhere near where we need to be in terms of getting close to fixing the energy crisis, nor to harnessing the true abilities of the sun in order to power our systems indefinitely. But we hope that one day that will happen. And the more energy and the more effort and the more focus and concentration we give to these areas, the quicker they bear fruit, essentially. It has been a long-standing trend in technology that we have been able to create things much faster than we predicted that we would be able to do so, simply because of interest and concentration in said areas. And with that, guys, I would like to say thank you for listening to my presentation. And please do your research when things like of this nature come about. Learn, read, and teach others so that everyone can have scientific literacy to the level of a physicist so they cannot be taken advantage of. And I thank you.
Okay, that was an excellent presentation from JAMSPARC President, Mr. Orion Green. What I learned, the power of the sun, palm of my hand. That's for all the Marvel fans out there. Okay, so our next presentation would be from none other than the Trinidad and Tobago Society for Physics Advancement, Research and Collaboration, TTSPARC. And this presentation will be conducted by our very own president, Mr. Brandon Qasim Mohammed. His presentation will focus on a very interesting field of quantum mechanics, which is already touched on a bit, but he will go in more depth in his presentation. So, Brandon, I'll allow you to take it away.
Thank you very much for that introduction. Firstly, I want to say that was a very well done presentation by our Jamaican sister body, Orion. So I thank you for sharing that. And as Jeremiah said, we are going to be talking about quantum computing. Now, before I share my slides, quantum computing has been an area of interest for me for the last 7 to 8 years, and I'm very happy to be sharing it with everyone right now. So are you all seeing this, right? You're not seeing this, right?
Yes, we can see.
Yeah.
Okay, great. So I just want to say again, thank you for having this, and thank you for having me. So what is quantum computing? Well, we first need to understand what computing is, right? So we understand what computing is because we have computers, we have phones, we have even in most basic computers that we have calculators. And these are things that do number crunching. These are things that allow us to do feats that we cannot do on our own. These are things that run in the background hundreds, thousands, or millions of times, things that we cannot do in the same amount of time. So why are we going into quantum computing if normal computing is already working so well? Well, we will get to that in a moment. But first, we have to understand what is the difference between classical computing and quantum computing. Now, classical computing relies on classical physics, whereas quantum computing relies on quantum physics. Yeah, right? Let's look at some of the things that are here. So as it says here, quantum or quanta simply refers to how much of something there is. In this instance, a small distinct quantity of matter and energy that a body can hold. So what that refers to is that in quantum mechanics, we have the idea or notion that energy cannot be continuous like how it was held in classical physics. It must be distinct. It must be quantized, where we get quantum from. And these packets of energy take integer numbers. And utilizing this, we can build quantum computing. So what is quantum computing based on this? It is the operation of controlling the behavior of this same quantized matter and energy, as it says, the fundamental particles, in a way that is different to traditional computers. So how is the way of operation different? Well, in classical computing, we have electrical signals that go in and allow for these things called bits. And these bits are made up of zeros and ones. So these things now can be typically electrons, or it is electrical signals. As many of you know, electrical signals such as 5 volts is typically a bit of 1. Electrical signals such as 0 is typically a bit of 0 or ground state. There are many different ways in which we can also have these ones and zeros, such as electron trapping for long-term storage, or as in the RAM, it is the electron shifting, so that we can use it in volatile memory. So if that is working well, then how do we now utilize quantum for quantum computing? Well, we utilize these things called qubits, and qubits, QU might give you an indication of what it stands for. It is quantum bits. And whereas normal classical bits can be a 0 or a 1, a qubit can be in a state between 0 and 1. And this is the power that we are trying to use so that we can increase our computational output and productivity from classical to quantum computing. Some of the things that we make use of so that we can utilize quantum computing is things such as superposition, where, as I said, the state of the quantum system can be in a state between 0 and 1. Things such as, sorry, the name is blank, entanglement. Things such as entanglement, where 2 quantum states can be entangled, and what happens is what is done on the other, or what is done on one, something can be done on the other, and that would allow for an increase in quantum computation. Companies already started to make use of these things, and as we'll see here in a moment, we have quantum computing in real life. Now, it is very, very important that we can utilize this in healthcare industries. I hope many of you know that there is this thing called protein folding simulation that must be done in chemistry and in biology to allow for the development of medicines. Well, one of the ways in which this is done is through massive supercomputers. Another way this is done is by people providing idle time on their computers to allow for the number crunching and protein folding of these things. Why this is important is because whereas classical computing can only do like 1 bit at a time, 1 piece at a time, and that's the reason why it takes so long, quantum computing can do multiple of these things at a time. It is probabilistic in its nature, and because of that, it can take multiple parts at the same time. As you see, a navigational service improvement, Google Maps. Due to the quantum nature of things, we can better pinpoint locations and all of that. Enhanced encryption overall improves security defense maneuvers. Now, the security that we have right now for RSA encryption, it is the idea that classical computers are very problematic when factorizing prime numbers. And because it is very problematic, we cannot factorize prime numbers properly, and it will take many years in order to factorize these things of prime numbers. These encryptions are very secure. However, because of the probabilistic nature of quantum computing, it can break these things very easy. Now, that sounds like it could be very bad. However, the flip side is also correct, where we can use these things to break these encryption and then build better encryption based on quantum computing. So we can enhance our encryption as we go along there. And lastly, artificial intelligence. Artificial intelligence runs on machine learning. Machine learning, it takes very long to do, and it needs to do 1 bit at a time, 1 piece at a time. As you can see already from the pattern that we have established, quantum computing, its probabilistic nature and use of quantum world, can enhance artificial intelligence and artificial intelligence training with machine learning. Now, it's not all rosy in the quantum world, because everything has its challenges, everything has its disadvantages. So what are some disadvantages of quantum computing? Well, as it says here, for different computational types, new algorithms would have to be written. Quantum computing often employs the use of special algorithms to function. Now, what that means is there are different platforms that we are trying to figure out what will work for quantum computing right now. There is gate-based quantum computing, adiabatic quantum computing. There is ion trapping quantum computing in silicon. There is ions and diamonds quantum computing. There is photonic quantum computing. And all of these different platforms have ways that algorithms can be made for them. The one that is most used right now is by D-Wave, and they make use of adiabatic quantum computing. I believe, and some correct if I'm wrong, that companies like IBM and Google make use of gate-based quantum computing, and I know that companies like Intel will be looking into silicon trapping ions quantum computing. So that is a disadvantage that is with the emergence of the quantum computing field right now. When a platform is established by whatever company that gets a good foothold, this would be less of a disadvantage. However, as it is right now, it is one. Quantum decoherence. Now, in order to understand quantum decoherence, we must first understand quantum coherence. Coherence is the idea of maintaining information in a quantum state. And this is very important because when this information is lost, or when the quantum state becomes decohered, its information is lost, and we must now establish the state again. We must initialize it. We must do all of these things so we can get the information back on it. Having a longer time means that we can work on quantum computers longer with longer information. And quantum decoherence is something that we are trying to fight against in order to keep that information in the system. And lastly, here we have privacy infringements. As I said before, because of the ability of quantum computers to break the RSA encryption, when it now comes out, privacy would be a thing that would need to be reestablished in the world because of its ease of breaking, and it will have to be something that we'll be need to be very careful and take particular attention and care to when it does come out. To end this, I would just like to show you a quantum computer that is from IBM right now, and as you can see here, it is huge. It is massively huge. These things are in chambers that are cooled to almost absolute zero to allow for superconducting ions so that they can use their qubits properly. And the state that quantum computers are in right now is the same state that classical computers were in back in the 60s, where a computer that would have these small amounts of memory and processing takes up entire rooms. And slowly, every day, bit by bit, these things are being improved. The temperature at which we can have quantum coherence has been increased, and hopefully as we get along to other platforms and other qubits, we can reach that point where we can have quantum computing done at our temperature, so we can utilize quantum computers as they are. I would like to thank you because this brings me to the end of my presentation, and I'd like to thank Anna and Kevin for preparing this for me, and I'd like to thank again everybody for putting forward this show because it is greatly appreciated. Thank you.
Thank you, Brandon. So that brings us to the end of the club presentations. And now we have the final question from Mr. Orin Green.
Right. So my final question is a really simple one. I think anybody who does or doesn't do physics could answer this one. What is cold? What is the concept of coldness? What is cold?
Interesting. Okay,
Yes,
so
very
5, 4, 3, 2, 1, go. And in the meantime, we will announce who did win at the end of these. Once the chat moderators say that they've received answers, we will announce who were the top 3 answers for the event. I'd like to ask that you contact the council via our Instagram page or our Facebook page, which would be what you are looking at the stream on currently. And we can get your prize to you via that way. So what is cold? Do we have any answers yet? We do not have any answers yet. What is cold?
Yeah, what is cold? I'm not asking you guys for cold objects, by the way. I'm asking, I'm asking, what's cold? How would you define cold in a physical
Maybe if we say it in a
sense?
different, maybe if we say it in a different tone, they'll get an answer.
Let's see. How could I say this? So, what is cold? Like, how would you define coldness? Right? Just like how would you describe a shadow, essentially? How would you describe a shadow or darkness? What is darkness? Right? Similarly, what is cold?
Darkness.
Yes, what is darkness? So what is cold? Similar analogies, you know? That should point you guys in the right direction. I believe so.
One correct answer obtained.
Okay, we got one correct answer. That's great. All right. So somebody's head was working. Love to see it. Love to see it.
Okay. So can our chat moderators let us know who are the top 3 respondees so that they'll know to contact us at the end of the event? In the meantime, I will say our closing address. So,
Amara, is that a question we have there from Orlando Riddick?
What?
Somebody could confirm. I'm seeing how much of revision do you guys put out to have a successful grade?
how much revision do we put out to have a successful grade? Actually, I will give that question to, I'll take it. So personally, I think that is really about time management. So being involved in clubs, it does take a lot of time away from being able to sit down and do work and hours. But I prefer to do focused work, so more of maybe 3 to 4 hours of focused studying rather than several hours of, you know, not really getting anything done and remembering things, just trying to memorize it. So in that time, it's really important to understand the concepts rather than try to memorize and just answer questions. That's me personally. I don't know. Yeah, go ahead, Mr. Matthew.
I will have an answer to that question. So to that, my short answer is that there is no fixed amount of hours you can take to study. It is really dependent on the course outline and what specific topics that may be your strong points or weak points. And of course, as Amara said, we have to balance club life. Even when you have labs and assignments and stuff, that kind of takes away time from studying. So it's really how much time you need to grasp a concept you take. What I do is that from every topic, I follow my course outline and I always tick off the topics that I know I would have a better understanding going forward, and I can kind of relax in green. So I highlight that in green. And then those ones that I know will be a bit challenging, I have that in red. And I do that for every course I do. I do physics and chem double major. Yeah, I do like myself. And that's how I get grades that I get, because I focus on what would be the challenging aspect. And then I allocate time accordingly. So it's really the proportion, very proportion dependent question. Hope I was able to answer it to the best of my ability.
Okay, so I see Mr. Brandon Mohammed and Mr. Rin Green with their hands up. Either of you?
Yeah, my 2 cents to that question would be to, in university, we need to stop thinking about memorizing, right? So I know back in Form 4, Form 5, Form 6, it was pushed on memorizing, but in the higher levels, we need to stop on memorizing and we need to start understanding concepts. Once you get to the basis of the concepts and you understand the concept, you can apply it wherever and wherever. And what I also mean by stop memorizing, we need to memorize, is that once you understand the concepts, it becomes very second nature to apply things. And when you do move on to learn other stuff and you come back to this, because you understood the concept, you can come back to it quite easier than if you just memorize it. So that would be my 2 cents in there.
Thank you, Brandon. Mr. Rin Green.
Yes, I believe Brandon is absolutely right, especially with like CAPE and CSEC. Coming from CAPE and CSEC, the exams are so formulaic that it's like doing a recipe over and over again. Once you memorize it one way, you think that that's how you always bake the cake or go about it. But it's very important to have an intrinsic understanding of what you are doing so that you can apply it well, as Brandon said before. So having an intrinsic understanding of like the photoelectric effect or different concepts as those, so that you can see them in every day, right? It shouldn't be a case that after you do a course or after you're done studying, all that is left of you is just, oh, I know what the formulas are, but I don't know what the formulas mean. I don't know what it means for reality. I don't know what it means for real life. You have to have that understanding, because if you don't have an intrinsic understanding, you can't be an agent of change. You can't change the status quo. You can't develop new phenomena. You can't make a difference or develop a new application without that understanding. So you have to understand. Another thing about studying is, let's stop looking at studying as a rigid thing. Let's start treating studying as being a supplement or a subcategory of our lives, right? Instead, so you can do what I do. So because I'm doing what I love as my major, I'm doing biomedical instrumentation, I can find times, because I live on YouTube, not really Netflix and those type of things, I can find videos that essentially, you know, put things into perspective for me, and I can listen to them, and then I have an understanding. So when I hear it in class, I'm like, oh, it connects. You know, it's all a circle. Everything is just a zoomed in version of what you've done before, right? You can always do that. And also what works for me in terms of studying is not essentially writing down things, but forming analogies, right? Using things that I go through every day and comparing them with what I'm learning in class to help solidify it in my mind so I can see it again. And if you find that writing doesn't work for you, maybe you're not a writing kind of learner. Maybe you're a visual learner. Maybe going on Google Images and seeing the different images of the concept can help to give you a different perspective or a new route of looking at things. So try different methods. It's not about how long you study, it's about studying effectively. Because I know many people, they studied the day before and they do the exam and ace it, and they still understand what they're doing. So you have to make sure that you study effectively, not long, right? All right, that's my 2 cents on that too.
Yeah, prioritize quality studying, not quantity studying, as Orion said. Just wanted to put a little phrase.
Great, thank you all. So our chat moderators did say who we have. However, we have a tie for 3rd place. So what we'll do, we'll have one more question. I believe either Mr. Matura or Mr. Green can ask one more question to break the tie.
All right, so here's my question. What analogy did Schrödinger use for his equation? So what famous animal is associated with Schrödinger, and what is it about? What is Schrödinger's principle about based on that animal?
I know the answer, but I won't say it. Let's see if anybody else knows the answer.
Yeah.
Who knows?
Everybody should know this
I might
question.
take it for
Yeah.
myself.
Yeah, I've been seeing this. I've seen this so much, and that's the thing about being a famous physicist or a famous scientist. You see these things so much in media that is like when you get to the level of actually learning, you're like, oh, I saw this in a cartoon, and now it's math, and I'm just like, ooh, I'm scared. You know,
Yeah,
it really catches you by surprise. Okay, we got our tiebreaker. Great,
Okay,
great.
wonderful. All right. Thank you, Mr. Green. So to end us all off, I'd like to express my sincerest gratitude to each and every one of you for coming out to support the Student Council in this milestone event. Thank you to the head of department, Dr. Sharma, all of our presenters, Dr. Hack, Dr. Joseph, Dr. Zuzikov, and Dr. Andrews, as well as the undergraduate and postgraduate students, Ms. Paul, Ms. Budu, Mr. Rajkumar, and Ms. Greasley, all of our attendees for taking time out of your busy schedules to witness history in the making of our first ever Physics Day. The event was recorded, so it will be available to view again right on the Council's YouTube page. We will sort that out after this. To the students, we hope that this event was enjoyable as well as informative to you. We hope that through this event, you see that any place in your life worth going to, there will be no shortcuts. It's going to be a difficult ride, but your success will be the sum of all the small efforts that you put into each day. Keep striving to be the best student that you are and can be. Newton's first law of motion states that a body at rest stays at rest and a body in motion stays in motion unless acted upon by an external force. I always used to forget that last part. Be the body in motion. Let your hunger for success drive you to be unstoppable. And with that, I'd like to officially close Physics Day 2022, Physics is Boundless. Thank you and stay safe, everyone. And thank you to my team as well, my chat moderators and everyone else associated that helped for this day to be a success. Thank you once again and stay safe, everyone.